All right, so we're on to case 4, the last of the 4 cases that we need to consider when we're doing partial fraction decompositions. And in this case, it's kind of similar to case 3. We're still looking at irreducible quadratic factors. The only difference now, though, in case 4 is that if q of x has irreducible quadratic factors, some of them are now allowed to be repeated. So if I have a factor of this form, ax squared plus bx plus c, where that is an irreducible quadratic factor, but it's also raised to some positive integer power r, where r is greater than or equal to 2, then that means we have repeated factors of this form. The way we deal with that is very much the same as how we dealt with it in case 2, where we had repeated linear factors. You have a sum of terms here, sum of rational expressions, where the denominators look like that irreducible quadratic, but starting out to the first power, and then to the second power, and then there would be a third power in here if r is big enough, and then we keep on going until we get to that same, oh, you know what, this should be a 2 right here. Had an r there, it should be a 2, where we end up with ax squared plus bx plus c, but to the rth power. The numerators here, which is what makes this different from case 2, are linear polynomials instead of constants, okay? So it's kind of like a combination of case 2 and case 3 that we're looking at here. All right, let's just jump into an example. Here I want to evaluate x squared, the integral of x squared plus x plus 1 over x squared plus 1 squared. Notice that the thing in parentheses here is a sum of squares again. We saw in the previous example a sum of squares appearing there, and we said that those are always irreducible. So this means that I can write my rational as x squared plus x plus 1 over, well, I'm just going to rewrite it first, actually, x squared plus 1 quantity squared, but I can write it in this form, ax plus b over x squared plus 1, where it's not raised to any power yet, or if you want to be really technical, I could say it's to the first power, plus cx plus d over x squared plus 1, but this time raised to the second power. And I stopped there because now I've gotten to the exponent that the original denominator was being raised to. Okay, similar approach as what we've been doing so far. I want to clear the denominators from both sides. Okay, so let's think about what that's going to look like. Multiply both sides by x squared plus 1 quantity squared. That eliminates this and this. X squared plus x plus 1 is all that's left on the left side. Now that x squared plus 1, because it's squared, one of those factors will cancel with that x squared plus 1, but will still leave me with the other one. So I have ax plus b times x squared plus 1 there. When I multiply this by this, I'm going to have the entire denominator cancel out, and I'm only left with cx plus d here, okay? And so now we have kind of a similar setup as the previous problem, where I have a factor of x squared plus 1 here, which the way we've been doing this is we've been trying to plug something in to make factors like this become 0. In this case, we need a complex number to make that work. If I set x equal to I, the imaginary constant I, if I plug that in here, I squared is -1 plus 1 is 0. That makes all of that stuff go away. But you will also need to be careful to consider what's happening on the with everything else. So plugging in I in on my left-hand side, I have I squared, which I know is equal to -1 plus 1 over here would be 0, and then plus I, that's what's getting plugged in for that x there. It all comes out to 0 plus I. Normally you wouldn't write 0 plus I, you would normally just write I. But I'm going to leave the 0 in there because remember, we have to end up equating real parts to imaginary parts. So it's helpful to remember what the real part is. It's that 0 right there. Okay, we plug an I in so that would go to 0, and that leaves me with that cx plus d, which when I plug I in for x is going to give me d plus ci. Notice I switched the order of those terms, and that's because we want the real part to show up first, the imaginary part to show up second. If I equate real parts, I get d equals 0. And if I equate imaginary parts, c is equal to 1. 2 down, 2 to go. All right, so now what do we need to do? I need to solve for A and B. And so in order to do that, it would be nice if there was something else that I could plug in that would help me solve. But the only real factor that was part of my original denominator, we've already kind of figured out how to make a 0 out of that, and it only gave us solutions for C and D. So when we ran into this wall previously, we said try plugging in other numbers, whether or not it makes things go to 0. But try to plug in numbers that we know tend to be nice to work with. For example, if I plug a 0 in for x, what's going to happen? My left-hand side goes to 1. What about my right-hand side? Well, if I plug a 0 in, first of all, here, plugging a 0 in is just going to produce a 1. And then notice the a times 0, this also becomes 0, right? Plus b is just b. So all of this comes out to b times 1, or b. If I plug a 0 in for this x, that term goes to 0. And then we already found out that d is also equal to 0. So all of the other stuff becomes 0, and I'm just left with b equals 1. Now there's only one unknown left. Okay? And we can approach this in exactly the same way. Pick a number that's convenient to work with, that's easy to work with, and try plugging it in. And then use the information that we've already accumulated. So I'm going to plug 1 in for x. 1 plus 1 plus 1 is what I get there, 3. Okay, what happens on the left-hand side? A is the only thing I don't know yet. So I can't say what that is, but I'm going to plug a 1 in, and I'm going to get a times 1, which is a, plus b, which I know is 1, right? So I'm going to get a plus 1. And then over here, I'm going to get 1 squared plus 1, which is 2. We'll kind of simplify that in a second. Plus c times 1. Well, c is equal to 1. Multiplying it by 1 is just 1. And then I have this d, which, again, remember, that's 0. Nothing really to write there. So let's keep working at this. 3 is equal to what? 2a plus 2 plus 1, which is plus 3. These cancel out, and I get 2a equals 0, so that a is equal to 0. Okay? So that actually is pretty nice. With 2 of our unknowns were equal to 0, which kind of simplifies the rest of the work. I like that. So now what does our integral look like? Well, remember, the first term here was ax plus b. A was equal to 0, so we lose this term. B was equal to 1. So I have 1 over x squared plus 1. I know right off the bat that's going to be arctangent of x. Easy one. Cx plus d. D was equal to 0. C was equal to 1. So this becomes plus x over x squared plus 1 quantity squared dx. Okay? So like we said, right off the bat, we know that this gives me the inverse tangent of x. This I can solve with a fairly straightforward u substitution. Set u equal to x squared plus 1, so that du would be equal to 2x dx. We have x dx. The 2 is easy to manage. Multiply both sides by 1/2. So this becomes 1/2. I bring that out. Du over u squared, right? Because that was raised to the second power. That's the same thing as u to the negative 2 power. The antiderivative of this is negative u to the negative 1 power. Or another way of writing that is this. So I have my inverse tangent of x minus, because a negative is going to come from this antiderivative, 1/2 times 1 over u. That's u to the negative first power plus c. That's equal to the inverse tangent of x minus, hold on one second. Sorry about that. 1 over 2 times u, but u is equal to x squared plus 1. So I can write that as 1 over 2 times x squared plus 1. And then I'm going to have my plus c there. Okay? So I've got that. That's my final answer. I have a plus C, so I know that I haven't forgotten that one step that people tend to forget, that constant of integration. Awesome. Okay, we have one example left to do. Let me get my notes organized here. I'm calling this rationalizing substitution. So what we're going to see here is something that's not actually a rational function that we want to integrate. It's almost a rational function. It's got this square root of x in here. Remember, rational functions can't have anything other than polynomials in their numerator and denominator. So because it's not a polynomial, it's technically not a rational function. And in order to deal with this, I'm going to make a substitution, like a u substitution, that changes this into a rational function. From there, we can use partial fractions on it. So the u substitution I'm going to make is this. I'm going to say let u equal the square root of x, okay, because I see a square root of x showing up in there. Now, if I were to square both sides of that, I would get u squared equals x. Finding my differentials, take a derivative of both sides, I get 2u du on the left and dx on the right. So this is going to give me some substitutions to make. Rewriting this integral right here, this is going to become dx on top becomes 2u du. Let's pull the 2 out, but I'm going to have a u there, and I'll end up with a du out there. 1 plus the square root of x, all quantity squared, becomes 1 plus u quantity squared. And now, even though we started with something that wasn't a rational function, we ended with something that is. So we can evaluate this using partial fractions. This is a case 2 kind of situation because I have a repeated linear factor in my denominator. So I have to go off to the side and figure out what the partial fraction decomposition looks like. This u over 1 plus u quantity squared is going to look like some constant over 1 plus u plus some other constant over 1 plus u quantity squared, like that. Okay? Same approach as always. Multiply through by the 1 plus u squared, so I get u equals a times 1 plus u. Hopefully you're able to see now where that's coming from. Here, kind of smudged that a little bit. I'm going to cancel that entire denominator and just get plus b. Okay, so now we're plugging in convenient values for u to help solve for a and b. The first thing that seems helpful is to plug u equals -1 in, because that's going to give me a 0 right here. U equals -1, that'll become a -1. That goes to 0. This is just b on the right-hand side. So we've got one of our unknowns. B is -1. Okay, now I don't have anything that I'm multiplying to this b here to plug it in and turn it into a 0. So this is where we just pick some other number, something convenient. I'm going to use u equals 0, plug it into both sides and see what happens. My left side becomes 0. That's equal to a times 1 plus 0, which is just a, plus b, which we've now found is -1. That implies that a equals 1. Okay, so I've got my unknowns. I can put them in here and solve for that. So now my integral becomes, don't forget that 2 out there, a over 1 plus u, which is in this case just 1 over 1 plus u, plus b, which was -1, so let's write that as -1 over 1 plus u squared du. Okay, both of these we've dealt with already in different forms, but basically the same thing. So this becomes 2 times what? That's a natural log of the absolute value of 1 plus u. Over here, this is just plus 1 over 1 plus u. Remember, you can do another substitution. I probably wouldn't call it a u substitution since we already have a u, maybe a w substitution or something like that. And then I'm going to get plus c here. Now, we don't leave it in this form because those u's need to be put back in terms of x. So remember up here, u is equal to the square root of x. Let's plug those in. 2 times the natural log of 1 plus root x. Notice that I ditched the absolute value bars, and that's because the square root of x will always come out to a non-negative number. And then if I add 1 to that, it's always positive. So this is always going to be a positive number in here anyways. The absolute values are redundant. And then I have 1 over 1 plus root x there, plus c. That's it. Okay, so sometimes, again, you have something that looks close to a rational function, but it's not, because it doesn't necessarily have polynomials. But with a carefully chosen u substitution, you can convert it into something that is a rational function, and then partial fractions is helpful, and then you end up where we did here. Okay, so that's it for 7.4.